Dear friends, going to see the third part of the chapter Reagents in Organic Synthesis. And here in this third part, we are going to see one oxidizing agent, that is osmium tetroxide. Here, osmium tetroxide is also known as osmic acid, which is commonly known as osmium tetroxide. It is prepared by the reaction of metallic osmium with oxygen, or in presence of air. Upon oxidation, osmium metal gives osmium tetroxide. And particularly, this osmium tetroxide is useful specially in synthesis of fine chemicals, and one more use, that is the structural determination. So let us see one by one. Hydroxylation of alkene is the most important use of osmium tetroxide. Here, hydroxylation means introduction of OH groups on the molecule. And particularly, synhydroxylation of alkene is occurred with the help of osmium tetroxide. Here, any alkene can be converted into 1,2-glycol. This is OSO4, osmium tetroxide. Alkene on reaction with osmium tetroxide give osmic ester, or it is also known as osmate ester. And this osmate ester, upon further reaction with tertiary butanol in presence of water, gives 1,2-glycol. Remember, here two hydroxy groups are from the same phase, so it is synhydroxylation. If they are opposite, then we may call them as anti-hydroxylation. But here, synhydroxylation takes place with the help of osmium tetroxide, and further, upon oxidation, we can we can break this carbon-carbon bond between those carbons which are attached to hydroxy groups, and we get two carbonyl compounds. And these carbonyl compounds may be aldehyde and ketone, or in some cases aldehyde or ketone. If both the alkyl groups are attached on the two sides of compound, then we get two ketones. If only one alkyl groups are attached, then two aldehydes. And if mixture, then we get mixture of aldehyde and ketone. Here, we can identify where the double bond of olefin or alkene was in the reactant upon observation of the product of the oxidation product of osmium tetroxide. So let us take one example. Here, this 2-methyl 2-butene. So 1, 2, 3, 4. This is 2-methyl 2-butene. Upon reaction with osmium tetroxide, this osmate ester is formed, and further reaction with tertiary butanol and water, we get this glycol, or we can say 1,2-diol. 1,2-diol. This 1,2-diol, upon oxidation, the bond between these two carbons breaks. As here two alkyl groups, this one is R, this one is R, then we get RC double bond OR. So here we obtained acetone, and here only one alkyl group is attached to the carbon of hydroxy group. So here aldehyde CH3C double bond O. So this is acetaldehyde and acetone. Upon observation of these two products, we come to know that the bond between 1, 2, 3, and 4, 2 and 3 carbon was double bond. When we take another example, 3 methyl 1 butene. This is 1, 2, 3, 4. 3 methyl 1 butene upon reaction with osmium tetroxide, cyclization to osmate ester, and further reaction with tertiary butanol and H2O, we get this 1,2 diol. And upon breaking or upon oxidation, we get this formaldehyde and one more compound, that is 1, 2, 3. So this is 2 methyl propanol. 2 methyl propanol. This is not acetone, but this is 2 methyl propanol, as the carbons of hydroxy group contain one alkyl group, and this is, so here aldehyde is obtained, and this do not contain any alkyl group, so formaldehyde is obtained. Upon the observation of this third and fourth, or the product of this oxidation, we come to know that there is the double bond between 1 and 2, or we can say 1, 2, 3, 3 and 4, 1 and 2 or 3 and 4 carbon atoms. So double bond is at the end of the molecule. In this way, we can locate the double bond in reactant molecule. So this reaction also forms a method for preparation of aldehydes and ketones. Here benzene upon reaction with osmium tetroxide, we get mesotartaric acid. Cyclohexene upon reaction with osmium tetroxide, we get cis cyclohexane 1,2 diol. Second use is hydroxylation of conjugated double bonds. So here acrylaldehyde, generally CH2 double bond CH, C double bond CH. Generally these conjugated double bonds are very difficult to be oxidized. But in presence of oxidizing agents such as hydrogen peroxide, osmium tetroxide can also oxidize such conjugated double bonds. And here is one example, that acrylaldehyde upon oxidation with osmium tetroxide in presence of hydrogen peroxide, we get glyceraldehyde. Here this double bond is converted into single bond, and OH, these two OH are introduced. This is glyceraldehyde. And these are the some more examples where alpha beta unsaturated ketone have been converted into alpha beta dihydroxyketone. Cinnamic acid is converted into phenyl glyceric acid. Remember, this malic acid is converted into mesotartaric acid. Here in all the examples, only double bond have been converted into single bond, and two OH groups have been introduced on the molecule. Third and the last use of osmium tetroxide is elucidation of structure. Here, upon oxidation, anthracene gives this tetrol. Here, this double bond and this double bond, which were formerly in the reactant molecule, they have been oxidized and we get tetrol. This tetrol, after further oxidation with the help of potassium ferricyanide, we get naphthalene 2,3 dicarboxylic acid. This is naphthalene and 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is the numbering. This is naphthalene, but product is 2, 3 naphthalene 2, 3 dicarboxylic acid. This is the product. This is the right structure. Upon observation of the product of this oxidation with the help of osmium tetroxide, we can conclude that this one ring, two ring, and third ring also have been fused linearly, and the structure of the reactant anthracene can be predicted. These are the uses of osmium tetroxide. Thank you.